So welcome everybody. Most of you know me here, but there are people online who don't know me. So I'm Brian Skidmore, and I'm deeply interested in astronomy and love giving talks on the subject. My subject today is the story of modern cosmology. So modern cosmology is the application of science to the entire universe. Normally I give talks on particular objects like black holes, supernovae. Today it's about the entire universe, and it's the science of that story. So the purpose is to tell you the history of the subject and to bring you up to date to our modern understanding of the universe. And what I've done is I've selected several of the major milestones. I won't be able to be completely exhaustive, otherwise we would all be exhausted and we'll be here for days. So what I'm planning to do is talk for about 45 minutes to 50 minutes. Might hopefully have some time for some questions, and then we'll have to be out of here at 2 o'clock. So let me begin. So I want you to imagine that there must have been a first human being who looked up at, who was secure enough to put their need for survival aside and to look up at the night sky and to wonder what it was that they were looking at. And this is the sort of thing they would have seen, because there would have been, of course, no light pollution save that of fire. They would have seen thousands of stars, and the planets wandering between the stars as well as the moon. But they would have also, and they would have had a sense that those things were individual objects. They would have also seen a band across the sky, which we refer to as the Milky Way. They wouldn't have known at all what that object was. And it was only realized what that was in 1610 when Galileo, who was often referred to as the father of science, a brilliant Italian astronomer, built the first telescope, pointed it at the skies. And what he realized was that that Milky Band consisted of millions and millions of stars. So now we have the concept that we live within this vast system called the Milky Way. And then in subsequent centuries, of course, the telescope improved significantly. This is a fabulous picture. And we're now in the 1850s, so some 240 years later. This telescope belongs to the third Earl of Rosse, and it's known, he was based in Northern Ireland. He was a brilliant man. He was president of the Royal Society, and he built some very large telescopes. This is the largest in the world at the time, and it's called the Leviathan of Parsonstown. It has a diameter of 6 feet 72 inches, and you can see the man at the top there peering through the eyepiece. And the crucial thing about this telescope is that it was beginning to see objects that had never been seen before. These objects on the right-hand side are Lord Rosse's diagrams of what were referred to as spiral nebulae. The word nebulae means cloud-like, so not like a star, but more diffuse. And these had structure, they had these spiral patterns, but it wasn't understood what they were. So if we progress now to the 20th century, this chap here, he's an American astronomer called Besto Slipher, not very well known, but he made a crucial discovery. What he did is that he took the spectra of those spiral nebulae, and by doing that, he was able to establish how fast they were moving either towards us or away from us, because the spectra is either shifted towards the red end, which is called a redshift compared to what you would see in the laboratory, and that's when the object is moving away. If it's moving towards us, you get a blue shift. But most of them were moving away, and he began to realize that these probably were objects that were external to our Milky Way. They didn't lie within the Milky Way. So he was one of the first people probably the first person to realize that. And you can see some of the sort of relative speeds. They're very high speeds with respect to the Milky Way galaxy. And on the right is a much older man demonstrating his spectra. Then we have the most famous person in 20th century science. In 1915, this is Albert Einstein. He announces his General Theory of Relativity. And what he does is he replaces Newton's theory of gravity with his own theory of gravity, the General Theory of Relativity. And this is fundamental because gravity is the great sculptor of the universe. And so what it is, in essence, is a complete change in Newton's picture of gravity. So Newton viewed space and time as completely distinct, and that events took place on a background stage of space, but that they weren't connected in any way. But for Einstein, space and time were connected in a very precise mathematical way, represented by this grid here. And massive objects like the sun here or the Earth make dints in this space-time. The idea being that an object like the Earth orbits the sun because it's moving within the dint of space-time, the depression in space-time caused by massive objects. And this is important for understanding the entire universe, because if we have curvature by massive objects, then it's possible that the whole universe has curvature. And it's not necessarily the intuitive flat space that we think of when we think of space. So this is one of the only equations in the presentation. There is an idea of a critical density, which is on the denominator of that fraction. And that's the amount of matter that you need to make the universe flat. I'll describe what flat means in a moment. And so if the overall average density of the universe, if the amount of stuff in it is less than the critical density, then you get an open universe, which is on the right-hand side. You get that curvature there. What that means is that parallel lines diverge, and any triangle that you draw on that surface, its internal angles will be less than 180 degrees. If the amount of stuff in the universe is greater than the critical density, then the entire universe will curve in on itself. And that means that parallel lines will converge, triangles will have internal angles less than 180 degrees. But crucially, if you were to a universe like that would be finite. If you were to travel in through that universe, you would come back to where you started from. So, and then there's a sort of boundary between them where you've got exactly the right amount of stuff in the universe to make it flat. And in that universe, lines remain parallel, triangles, the internal angles add up to 180 degrees. Both the flat universe could be finite or infinite, and the open universe is infinite. So it turns out, spoiler alert, that we actually live in a flat universe. But still astronomers are not clear whether that implies the universe is infinite or finite. So what Einstein did is he was the first person to come out with a paper on cosmology that applied his theory to the entire universe. And his point of view was that the universe was static, that it wasn't changing. And therefore, he realized that if he had matter in his universe, that it would just simply collapse. So what he did is he added a fudge factor to his theory, what we call the cosmological constant, which kept it in balance. He was later to regret that and call it his biggest blunder, but actually it turns out to be fundamental to our understanding of the universe. And that's typical of Einstein, to do what he considers to be a mistake, but it was actually a brilliant move. We'll come back to that later. So a bit later, these two gentlemen, Friedmann and Lemaitre, use Einstein's equations to realize that they're consistent with an expanding universe. Friedmann did this in 1922 before anybody realized that the universe is in fact expanding. And Lemaitre was the first person to consider that actually, if everything is expanding now, then they were once at a very hot and dense state in the beginning. And he called this his primeval atom. So that gentleman there on the bottom left-hand corner is the inventor of the Big Bang theory. And he was also a priest. You can see the white collar that he has around his neck. And that was contentious at the time, because many astronomers believed that the universe was infinitely old. And if you had a priest saying that it was of a finite age, then he was implicitly suggesting there was a God creating the universe, and that caused a bit of tension. He was once asked how he managed to reconcile his scientific understanding with his belief in God, and he said, well, I took there are two paths to the truth, and I took both of them. So this is the most famous man of the period, and he takes a lot of credit for discovering the expansion of the universe. But as I've described, there were other people who took a fundamental role. Edwin Hubble on the left-hand side, the man after whom the Hubble Space Telescope is named. He, in 1923, discovers that what was thought to be a spiral nebula, in other words, a spiral object, but possibly in our galaxy, was actually outside of our galaxy. This is the discovery plate on the right-hand side. And he's labeled a particular star where he's put var, exclamation mark. What he's saying is that he's discovered a Cepheid variable. And there's a mechanism by which a Cepheid variable will tell you how far away the object in which it's embedded is away. Because the Cepheid variable has a particular pattern of variability. And the period of that variability is proportional to how intrinsically bright it was. So he knew how intrinsically bright that star was. He could measure how bright it appeared and calculate, therefore, how far that galaxy is away from us. And this is a modern view of that galaxy. This is the Andromeda galaxy. And he demonstrated that was definitely a separate island universe, as it were, a separate galaxy to the Milky Way. And so this galaxy teaches us our place in the universe. That suddenly the Milky Way is not everything, that there are other separate galaxies. One of the most momentous discoveries in astronomy. So you then have what we then have is this Hubble-Lemaître law, because what Hubble did is he used Slidfor's data to establish the distance to various galaxies, and determined through this plot. He plotted velocity on the vertical axis and distance on the horizontal axis, realized there was a straight line relationship between them, and came up with this law, which is a very simple law, but it's a fundamental one. And that h0 is the constant in that equation, and that's one of the key parameters in cosmology, and effectively measures how fast the universe is expanding. There's been a tremendous debate about what its value is, and there is still a debate today, as I'll mention later. But effectively, what it's saying is that if a galaxy is so far away, it will go at a certain speed. If it's twice as far away, it'll be at twice that speed. So, what the expansion of so we have now established that the universe is expanding. This doesn't mean that the individual objects within the universe are expanding. So the reason why our galaxy isn't expanding, is because the stars in the galaxy are all gravitationally bound together. None of them exceed the escape velocity of the Milky Way, and so they remain together. But distant galaxies from the Milky Way do follow that expansion, but you have to go to 10 to 20 million parsecs away to get that impression, that overall expansion. It also, for the same reason, this table doesn't expand the expanding universe, because its atoms are bound together by electromagnetic forces. And it means, in particular, it means that you are not expanding either. If you are expanding, then you can't use the universe as an excuse. So now we have the understanding that the universe is expanding. Again, a tremendous discovery. So the next stage in the story, we now reach the 1930s. And this gentleman on the left is Fritz Zwicky, who was a Swiss astronomer. He was brilliant, actually, brilliant career, but he was also quite an extraordinary personality. He was looking at this beautiful cluster of galaxies you see on the right-hand side, called the Coma cluster. And what he realized, he measured the relative speeds of the galaxies between it. He measured the speeds of the galaxies, the radial speeds of the galaxies, by looking at their spectra. And what he realized is that they were moving far too fast for the amount of matter that was actually there. What he concluded was that there was a huge amount of unseen matter in that cluster that you couldn't see just by looking at the stars, and we referred to it as dark matter. We still refer to it by that name. His estimate was much higher than the modern. He thought there was hundreds of times as much matter. We now think there's about 6 times as much matter. It was the first piece of evidence that there is more to the universe than meets the eye. And this is a sort of general principle in science, that our intuition and our perceptions can be upset by reality. That reality is often very different from our intuition. Incidentally, the Zwicky tend to have a rather fractious relationship with his colleagues. He inevitably looked down on them a little bit, and he often referred to them as bastards. And the ones he particularly disliked, he called spherical bastards, because they were bastards from whichever direction you looked at them. So there is other evidence for dark matter, and it turns out that when we look at galaxy clusters and we look at spiral galaxies and other galaxies, they don't behave according to the laws of physics that we would expect. They don't seem to behave Newton's or Einstein's laws, and it's because of this it's hypothesized to be this dark matter that I mentioned earlier. So there's another experiment, another piece of evidence. It's that if you look at a spiral galaxy, particularly one that's almost edge on, what you can do is you can measure how fast that galaxy is rotating at different distances from the center. So you see here a graph superimposed upon the triangular galaxy, a nearby galaxy to ours. And you can measure, based upon the stars and then later the hydrogen that you can't see in this image, astronomers can measure the radial velocity of those components. And you can see that the upper graph are the observations, but the dashed line is what you would expect if only the stars were present. And those lines are very, very different. That dashed line is very similar to what you would get in the solar system as well, if you were to measure the linear velocity of the planets from the sun. And so this is the second crucial piece of evidence that there is more to what you see than the stars present there. Second piece of evidence, very important. So progressing now to something important called gravitational lensing. So in Einstein's theory, objects will bend, that dint in space-time that I mentioned will change the path of light rays. There is an effect called gravitational lensing, which Einstein himself predicted, which means that if you have a massive foreground object, that will bend the light of objects behind it around the object, and therefore act as a lens. And it will also distort those objects. So if you look at these curved lines here, these curved objects, these are what the foreground cluster is doing to the background light. It's distorting it significantly. And we see these in many images from the Hubble Space Telescope, of which this is an example. One of my lecturers actually at university was the first to discover gravitational waves. And that's important for this image, and this is meant to be the smoking gun for the idea of dark matter. It's a bit much to take in, but it's called the bullet cluster. And the idea is that you have two clusters of galaxies, which you can, sorry, I've actually labeled this slightly. The galaxies are labeled there, and you have these two, what's happened is these two clusters of galaxies have passed through each other. The red is the gas that has been dragged behind, because that suffers friction. The galaxies effectively pass through each other, but the gas in the galaxies gets dragged behind. Now, what's happening is that you can't see very much, but there's a lot of there is a lot of distortion of background objects in this image. And what astronomers have used those distortions to do is to map where all the matter, dark and normal matter, is in a diagram. They're color-coded the dark matter blue, and it's that. So most of the matter is actually the blue regions, and that's meant to be the dark matter that has passed through the galaxies. But we know that matter can't be normal matter. There's just no credible explanation. That, one idea is that there's millions and millions of black holes, but you can't make that fit with the number of massive stars that could produce those in the universe. There just aren't sufficient numbers. So it's thought to be some sort of exotic particle which hasn't yet been discovered, and it's one of the great campaigns in astronomy is to establish what the dark matter actually is. There are many observatories around the world trying to do this, but it's very difficult. And it's a very odd substance because it doesn't interact. It only interacts gravitationally. It doesn't heat up. It doesn't interact with light, so it can't be detected that way with normal telescopes. So, and here we have an illustration of, it is an illustration, it's not a photo, of the Milky Way being embedded within a halo of dark matter. So when you look at images of galaxies, clusters of galaxies, then it isn't empty space between them. It's meant to be filled with this dark matter surrounding them. And it's thought to be fundamentally important for creating the structure of the galaxies over time in the universe. It's not actually, there is an alternative idea that there's an alternative theory called MOND. So not everybody believes, but most astronomers believe that dark matter is made of particles. So moving on now, sort of really to the 1950s. So in the 1950s, it's realized that the Big Bang itself created certain elements, and most of the elements of the periodic table are created by stars. But amazingly, between 10 seconds and 20 minutes from the beginning of the universe, which just seems extraordinary to be talking about such small times, the protons and the neutrons, which had formed at this time, began to form nuclei, and each atom has its own kind of nucleus. And so we have, from the left to the right, deuterium, helium-4, helium-3, and lithium-7. It's one of the great successes of the Big Bang theory that it correctly predicts the abundance of these nuclei in the universe that we see today. And in fact, it's a very sensitive, the relative proportion to those elements is a very sensitive function of the amount of dark matter is in the universe. And the theory very firmly says that the amount of dark matter is 4.6%, or approximately 4.6%. And so this is another, the amount of normal matter in the universe is only about 4%, and therefore much of the rest of it has to be dark matter. And that's another key to proving the existence of or demonstrating the existence of dark matter. It can't be normal matter. So now we have the Men in Black in the 1960s, and these two gentlemen make a momentous discovery by accident, and for that they win the Nobel Prize 14 years later. So it was a good day for them. What they were astronomers, what they were doing is looking at the hydrogen in the galaxies. In our galaxy, you may remember when I showed that rotation curve picture of that galaxy, that also was a plot of hydrogen and the speed of hydrogen in that galaxy. But they were mapping hydrogen in our galaxy, and they were using that antenna behind them at Bell Labs in New Jersey. What they were doing is they were using state-of-the-art receivers, but wherever they pointed their antenna in the sky, they received a background signal that they could not get rid of. And they tried everything. They looked at all their electronics. They even walked into the horn and found that pigeons had pooed inside the horn and decided that that was probably the source of noise. And in their paper, they wrote that they removed a white dielectric material from the inside of the horn. And it didn't remove the signal. They even sent the pigeons to a pigeon fancier as a sort of, can you take these off our hands? And he said, well, these are useless, let them go. And they were homing pigeons, so they flew back. Really annoying. So they actually got a technician to shoot the pigeons. It was okay in 1964. It's probably not okay now. But anyway, what they discovered was the afterglow of the Big Bang. Effectively, it's like looking at the glow of an explosion. I'll describe what it is on the next slide. So that's Robert Wilson on the left and Arno Penzias on the right, and they are immortal in cosmology. So it turns out that at the time it was just a uniform glow all around them that had no structure. So it sounds pretty boring actually, but it's fundamental. I'll explain why. Turns out that astronomers had already proposed, theoreticians, people who work out how the universe should behave, had already proposed that there must be this glow in the 1940s. George Gamow, Ralph Alpher, and Robert Herman. But they didn't win the Nobel Prize, which is a bit unfair. Anyway, they predicted it, and they realized that there must be within in this what's called the cosmic microwave background now, there must be structure from which everything is derived, including us. It couldn't be completely smooth. It seemed to be smooth, but it couldn't be. And that motivated the launch of several spacecraft over time. So in the late 80s, I remember this one, COBE, the Cosmic Background Explorer, was the first to map structure in the CMB. It's very difficult to see from Earth. It absorbs, the atmosphere absorbs the microwave region where this radiates. And then you have the Wilkinson microwave, not Microsoft, anisotropy probe, and then followed by Planck in 2009 to 2013. And these map the CMB to more and more accuracy. But what these maps are showing is the relative at the time this was formed, this radiation was formed in the universe, the structure in the matter. So in the red regions, you've got relatively dense parts of the universe, and in the blue regions, relatively rarefied regions. And this is the beginning of structure that we see all around us. So this is the full map. This is the map produced by Planck, the Planck spacecraft. And astronomers have calculated using the Big Bang theory that this first appeared 380,000 years after the beginning. And it exists because prior to that point, light could not escape, could not freely stream through the universe, because the universe contains charged particles, protons and electrons. And it was only when the universe cooled enough for those to bind together did we have neutral atoms, which meant that light could freely stream through the universe. So this is the very first light that is possible to see. It is not possible with conventional telescopes to see further into the past. This is what I was saying. So really, to recap, fluctuations there lead to what we see today, including you and I. And this is a really tricky slide to understand, and I'm not going to try to go into too much depth because you don't really need to. What this characterizes is that structure. So that structure there on the left, those fluctuations can be characterized in this way. It's called a power spectrum for those of you who understand these things. And it's effectively like doing a Fourier analysis of a wiggly line and splitting that into sine waves of different amplitude and phase, but doing this on a sort of angular scale, in an angular way all around us, splitting it into what are called the Laplace spherical harmonics. But anyway, you don't need to understand that. What this is really saying is that there is structure at different angular scales. So at the bottom here, on the horizontal axis, you've got different angular scales. So you don't need to, as I say, really understand the graph. But this is such a minefield of information. It's one of the most how should I say, the most accurate way that it's the key really to cosmology. So it turns out that the position of this peak tells us that the universe is flat. In other words, that the amount of stuff in the universe is precisely the amount you need to make the universe flat, not curved in on itself and not open, as I described earlier in the presentation. That the ratio of these two peaks tells us that the amount of ordinary stuff in the universe accounts for only 4.4% of all the matter and energy in the universe, and that the overall shape of these wiggles, that the total amount of matter, dark matter and normal matter, accounts for 27%. So you might think, well, what about the rest of it? And I'll tell you about that in a moment. So it's a bit of a surreal slide, but anyway, the previous one was pretty surreal. There's some pretty mind-bending concepts going on here. So what this is trying to say is that it was realized that if you look at the Big Bang theory, if you look at the universe, then there are some things about it which would seem to be incredible coincidences, and they're called problems in cosmology. One of them is the flatness problem. So when we look at the CMB, as I showed you before, astronomers have found to a very high accuracy that the universe is flat. But it turns out that if the universe, when it was created, was even a slightly away from flat, in other words, it had slightly too much matter in it or slightly too little, then it would diverge from being flat as time went on, extremely quickly, as sort of illustrated on the left-hand side here. So it's analogous to finding the universe like it's analogous to finding a pencil just sitting on coming into this lecture room and finding a pen sitting on its end like that. You wonder how that could possibly happen, and it's actually much more serious than that, because the pencil would have to be accurate to one part in 10 to the 30. So we find the universe to be flat, and that's actually turns out to be an incredible coincidence. And the other one is that the CMB, the cosmic microwave background, is the same temperature all around us. And by 300, when it was released at 380,000 years, much of it couldn't have been in contact with each other. So the fact that it's the same temperature all around us is another problem, which begs for an explanation. And the Big Bang theory, by its own, doesn't explain it. This is called the horizon problem. So the explanation that was put forward, and this happened now in the early 80s, so it now jumps to the 1980s. Alan Guth was a young particle physicist at CERN, the Centre de Recherche Nucléaire Particle Accelerator, and he was a theoretical physicist, and he proposed that the universe underwent a spectacular period of inflation right at the beginning, a vast amount of expansion over an incredibly short amount of time that's shown schematically here on the left-hand side with that sort of bright band sort of light at the beginning. So the idea being, sorry, it's a slightly unclear diagram, but essentially from the left-hand side to the right-hand side, the universe expands. The yellow circle refer to the amount of time, the horizon, in other words, the sphere of light that flows away from. That's what light would do if light could flow freely. In other words, the causal horizon, if you like. But that the actual universe expands much faster. So that what that results in is that the universe becoming flat, because any wrinkles in the universe would be blown out massively. It's about, I think it's about 10 to the power of 50, the amount of expansion that is underwent in inflation. And that's equivalent to a full stop expanding to larger than the size of the observable universe in about 10 to the minus 32 of a second. So this is taken seriously, but it's a breathtaking idea, and it solves the two problems that I just outlined before. So it's still a hypothesis. A lot of cosmologists do think this is right, but there are some dissenters, and it's quite controversial. But it does solve these two what are called fine-tuning problems that I described earlier. I don't know if that's clear or not, but anyway. So what we're saying here is that in the first 10 to the minus 32 of a second, the universe expanded by 10 to the power of 50, which is 1 followed by 50 zeros. So now move on to the late 90s, and astronomers are realizing that there's a contradiction between determining that the universe is flat and finding that the total amount of matter in the universe only accounts for something like 28%. And what two groups of astronomers do is they try to establish what the expansion of the universe has been doing in the relatively recent past and over the past 4 or 5 billion years. But what they need to do is they need to be able to have what are called standard candles. In other words, objects have a known brightness, known intrinsic brightness. They measure their brightness, and then they can determine their distance. So it's one of the most difficult things to do in cosmology, is to measure the distances to objects. So there are objects in the universe called Type 1a supernovae, where the remnants of the first star in the middle, It's ended its life. It's ended up as a white dwarf, which is what the sun will do in 5 billion years. It has a partner star, which is still burning, still in its normal phase. And the intense gravity of the white dwarf is pulling material from the other objects. And it's known that if that continues, if the white dwarf goes over what's called the Chandrasekhar limit, the star will explode violently to what's called a supernovae. And these supernovae can be seen right across the universe. An individual one of these will easily outshine the galaxy in which it's contained. And so what these two groups did, there was one called the Supernova Cosmology Project and the other one called the High Z Supernova Search, is that they plotted the distance, which is on the x-axis, with the brightness. Brightness is actually dimmer as you go up. What they realized was that this demonstrated that not only is the universe expanding, but that it is expanding at an ever-increasing rate. It's actually accelerating in its expansion. This is a profound discovery. And the idea being is that it meant that the reintroduction of Einstein's cosmological constant, there is a sort of repulsive gravity going on in the universe. It's an energy that is a property of space itself, nothing to do with matter. And the idea is that the energy of space itself causes this acceleration. It hasn't been occurring since the beginning of the universe. It's been occurring since about 7 billion years ago. So in this diagram, the Big Bang occurs at the bottom and time is vertical upwards. And originally there would have been this massive inflation that I described earlier. Then there would have been a substantial slowing down of the expansion, because at that point the universe was dominated by matter. But as the universe expanded, the energy inherent in space itself began to dominate. It dominated about 7 billion years ago, and that meant that the universe changed from slowing down to then speeding up and speeding up and speeding up, and it's still speeding up today, and it's thought. But the baseline, the sort of model for the universe is that it will continue to do that forever. So this is extraordinary, and it was called dark energy. That's its name. So now, on the left-hand side, this is a sort of summary slide to give us the sort of inventory of the universe. And these are sort of 2015 figures because they're derived from Planck. So on the left-hand side, we have the inventory of the universe. Only 4.9% of the stuff, the matter and the energy in the universe is normal matter, the stuff that you and I are made of, atoms and so forth. 26.5% is made of dark matter, still mysterious, still not understood. And the rest of it is dark energy, 68.86%. But it's a bit embarrassing because we don't understand 95.1% of the universe. The Hubble constant I mentioned earlier is this figure, not 42, but 67.74. The universe is flat with a very high degree of precision. The age is about 13.8 billion years, which you can derive from Planck data. That's a really obscure thing to say, the equation of state. What that means is that if that figure W is -1, then the universe will simply, the energy of space is constant and the universe will simply accelerate forever. But if it's different from that number, the universe could either eventually collapse or go into something called the Big Rip, which I'll mention in a moment. Anyway, so changing tack slightly, this is gives you some idea of the structure of the universe. This is a survey of galaxies called the Sloan Digital Sky Survey. And it's a survey of nearly 1 million galaxies, with the Earth is at the center. And this is 2 slices of the universe. And you can see that the structure of galaxies in the universe is filamentary. Galaxies don't fill the universe uniformly. There are walls, sheets, and voids within the structure. So I've got a nice animation to illustrate this, actually. It's a fly-through of that data, but a 3-dimensional fly-through. If it works, because animations have a tendency to play up when it comes to importance. Of course, it's not working. There we go. Relief. There's no sound. This is a rather wonderful fly-through of the universe. These are real positions of galaxies according to the survey. You could never do this because you'd have to travel millions of times the speed of light, but it is very evocative, I think. And all of this comes from those tiny fluctuations in the cosmic microwave background. And those, I forgot to mention that those fluctuations are only 1 part in 100,000. But it's thought that dark matter is essential because without dark matter, they couldn't have evolved into the structures that we see today. And so, 100 years ago, we thought we were the only galaxy. Billions and billions of them. And in fact, there could be an infinite number because we know the universe is flat. There could be an infinite number. That's the simplest explanation. Any idea? That's effectively. So this is the big picture. We're sort of coming now to sort of the conclusion, really. So this is the overall picture. We have the Big Bang, not fully understood, a singularity that physics can't quite reach. We don't have a theory of the bang itself. The Big Bang theory is not a theory of the bang itself. It's the rest of it, what happened after the bang. 380,000 years, says 400,000, 380,000 years. You get this here. It's called recombination. That's a misnomer. It's actually decoupling. So that's when light was able to freely stream through the universe, and that image that there is the cosmic microwave background that I mentioned before. Then we have neutral atoms. Remember I said that electrons combined with the nuclei to form neutral atoms. This is known as the dark ages because the atoms by themselves don't produce light until they form stars. This is called the dark ages. Then we have the formation of the first astronomical objects via gravity. Gravity creating stars, creating galaxies. So the stars reionize the universe. That means that they heat up the universe and electrons escape from the atoms. So it's similar to this position here before the atoms formed. Then the universe is fully ionized, and then you get the formation of galaxies in a billion years since. So this is a lovely picture. This is one of the images of the cosmos from the James Webb Space Telescope. It's exquisite. I've seen this with Lee. Is Lee here? Lee and I went to see Brian Cox at the Royal Opera House on the 1st of August, and it was fabulous. And he showed this image, but he showed it on the biggest screen you've ever seen. I can't do that. And even though it was a vast screen on an enormous resolution, there was no pixelation at all. It's an extraordinary image. You can see all these beautiful galaxies, far more than you could see with the equivalent picture with the Hubble Space Telescope. And you can also see the distortion of background galaxies here, these these filaments and arcs. And that's caused, these are much further away than these foreground objects. And what astronomers have found already is that these objects are far more involved than they expected, that their spiral structure is much more mature than was expected. And it's surprising that some of them are only a few 100 million years after the beginning of the universe. And that's really what's taken astronomers by surprise. There's a lot more work to be done. James Webb has done some work on these sort of images, but it's moved on to other things, and it will need to do longer exposures. There'll be further science campaigns in the future to look more closely at this. But this is gold for astronomers and cosmologists. This is an object that is one of the earliest objects in the universe to have ever been seen, only 700 million years after the beginning. And this is just a close-up. You can see the extraordinarily beautiful galaxies. So one of the original motives, in fact, for the James Webb Space Telescope was to make it infrared, because the early universe, although it itself was shone in the ultraviolet, it's been stretched by the expansion of the universe. So we see it now in the infrared, the galaxies that are formed. We go backwards. These galaxies that originally formed here from the Dark Ages, we now see them in the infrared. Hubble can't do that. They can only see in the visible, so it doesn't see the earliest galaxies. Now James Webb is showing us these very first galaxies that we've never seen before. You might imagine that James Webb sees further than any other telescope, but that's not true, and it will never be true because this is the furthest point that you can see. And that is only possible with microwave spacecraft that can see in the microwave region, like COBE, WMAP, and Planck that I mentioned earlier. But it's this area actually that we know least about. So let me go forward. So what of the future? A few more minutes. So on the left panel here, we have something called the heat. What will happen to the universe in the far future? Well, the sort of baseline idea is actually the energy of space, the dark energy, which we don't understand properly, but the dark energy is constant. The dark energy density is constant with space, and what that means is that the universe will simply accelerate and accelerate and accelerate forever. And that means that galaxies will drift apart from each other, and that ultimately no galaxy will see any other galaxy which it's not gravitationally bound to. And it also means that there will be the stars will eventually consume all the material from which they are made, and when a star dies, it actually locks up much of its material inside it, so it isn't all recycled, and there won't be the sort of gravitational gradients over time to produce more stars anyway. So there will be some hydrogen floating around, but it won't be able to form stars. So you ultimately get this sort of very boring heat death where no life can exist, no new stars are being created, and everything just reaches thermodynamic equilibrium. On the right-hand side is a concept called the Big Rip, and this isn't thought to be the case, but it could be, because I don't know if you remember, I won't go back, but there was a parameter in that wiggly line slide. There was a parameter called W, and if that is less than minus, it's the observed value is consistent with -1. But if it is less than -1, then the universe will go into what's called a big rip, and the energy of space itself will increase over time. And what that will lead to is, in the future, the galaxy clusters will be erased, the Milky Way will be destroyed, the solar system will be unbound, the Earth will explode, atoms will be ripped apart from each other, and then the big rip is meant to be in 35 gigayears time, which is where all matter is ripped apart. So that's a bit of a scary future. We won't be here to think about it, but anyway, it's a possibility. There are a few outstanding problems. Cosmology. I need to finish it. What are dark matter and dark energy? Don't know. There's an amusing issue with dark energy that it's meant to be the energy of the vacuum, and when theorists use their theories to calculate the actual energy of the vacuum and compare it with what they observe, they find that it's out by a factor of 10 to the power of 120. So that's 1 followed by 120 zeros, and it's considered to be the worst prediction in all of physics. Is the universe finite or infinite? So we think it's flat, but the most likely explanation is that it's infinite, but you can have a finite flat universe because so if you play asteroids, for example, in your spacecraft, your little spaceship in the middle, if you fly it off to one end, it will come back on the other side of the screen, and that geometry is called toroidal geometry. So it's like a tire, like a donut. And although a donut looks curved, actually it's flat geometrically. So the universe could be a toroidal shape, or a toroidal geometry, I should say, in which case it will be finite, but the baseline is that it's infinite. Why is there something rather than nothing? This is an issue to do with matter and antimatter. At the beginning, it's thought that equal amounts of matter and antimatter were created. So how come there is anything at all? It should have all annihilated. it should have annihilated each other. Matter and antimatter should have annihilated, and yet here we are. So how is that explained? And are there an infinity of other universes? This is been raised as a possibility that this isn't the only universe, that there could be an infinite ensemble of other universes, each with different properties, some of which give rise to life, some of which only last for a few seconds, all sorts of bizarre properties. And one interpretation of quantum mechanics is also that there is an infinite ensemble of other universes as well. So maybe that's true. So to sum up, really, what cosmology is at its heart is a desire to understand our origins. Where do we come from? It's an attempt to answer that yearning that human beings have. And it's astonishing that we know that the universe is 13.8 billion years old. We know that the Earth is about 5 billion years old, and that life got going about 3.5 billion years ago. And in a sense, I was thinking yesterday that the search for cosmology, the search for origins in cosmology and life are very similar in the sense that we can't quite get to the origin. We haven't yet got a theory of the beginning of the universe, so we haven't yet got a theory of the beginning of life. And then life carries on. We appear about 3 million years ago, and then it's only within the last. Then we evolve. We evolve consciousness, and we develop the understanding, begin to understand the universe seriously only in the last 100 years. So we've got 13.8 billion years. Miracle after miracle after miracle, and here we are with our knowledge of the universe after only about 100 years of endeavour. And I think that is a real testament to the science and human ability. And I think it's a real, we're the only species as well. Of the millions of species on Earth, we're the only ones who contemplate the universe. So cosmology is really, in a sense, what makes us human. The ability to look at the universe and wonder about it is what makes us human. There's something beautiful about it, and there's something inspiring about it as well.